Hey everyone. Okay, so this begins part 4 of our little series here, which is also the last part. So 3 last videos included in here will be combinatorics, which is what we're about to do. That's just a fancy way of saying perms and coms. And then probability, and then we'll end our time together with a video on game theory. Okay? All right, so first thing is combinatorics. That's what we want to deal with in this video. And again, combinatorics is just a fancy way of saying counting methods. Your teacher may have called it counting methods, or they may have called it permutations and combinations, okay? All the same thing. So let's talk about a little bit of vocabulary first. Again, this guy here, this yellowish greenish thing, is all of the stuff you have available to you on your formula sheet, okay? Okay, so things we got to talk about here. The fundamental counting principle, first of all. The FCP states that if a task is made up of individual steps or choices, the total amount of possibilities for the task is given by multiplying the choices of each step together. So if I had 2 pairs of pants and 3 shirts and 2 pairs of shoes, and I was trying to figure out how many outfits I could make. If an outfit was a pair of pants, a shirt, and a shoe, I just multiply that 2 by that 3 by that 2. 2 times 3 is 6 times 2 is 12. So I could have 12 different outcomes. That's all the fundamental counting principle is saying, okay? A factorial represents the product of a number and every previous natural number before it. So that guy there is my n with an exclamation mark right here. Okay, so if that n was 10, 10 factorial or 10 exclamation mark would mean 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. You just keep going to the previous one, to the previous one, to the previous one, until you get back to 1, okay? Okay. A permutation is an arrangement of a set of objects in which changing the order produced different results. Okay, so if this is Sally, and this is Timmy, and this is Peter, and I took a picture. Here's Sally, here's Timmy, here's Peter. Okay, but if this was Peter, and this is Sally, and this is Timmy, that's a different picture. So changing the order changed the picture, so it produced a different result. Often, as teachers, we say, do I care about the order, or does order matter? And those are great things to say. I say it all the time. One of the things I've noticed with students, though, is when I say, does order matter, they hear, do I care about the order? Lots of these things you don't care about at all, right? Who cares whether Sally's beside Timmy or Timmy's beside Sally? That's not the point. The point is, if I switch places, do I get a different result? Okay, is something different. Be careful with identical items. You will need to divide out the arrangements of the identical items as they don't end up producing a different result. So if I had school and I wanted to know how many ways there were to arrange the letters of the word school, I have 1, 2, 3, 4, 5, 6 letters. So that would be 6 factorial, 6 times 5 times 4 times 3 times 2 times 1. But I have 2 O's, which means there'd be 2 factorial involved in just those 2 O's switching. And when I switch those 2 O's, I don't get a different result. So I divide out my identical items or my repeat items, okay? All right. A combination is a selection of a set of objects in which changing the order does not produce a different result. So things like, if I had pears and apples and bananas, and I was going to make a fruit salad, okay, whether I put the pears in, then the apples in, then the bananas in, or whether I put the bananas in, then the apples in, and then the pears in, that's still the same salad. I still have those same 3 vegetables. I still have those same 3 fruit mixed up in my bowl, okay? So things you're looking for here, look for words like group or handshake, selection, or committees, as long as the committees doesn't have titles. Okay, that's why I said committees of equal members. In a permutation, you were looking for, I didn't go through that list. Let me go back with you for a sec. You'd be looking for words like lineup, arrangement, or list, or committees with titles. Okay, so that's the difference in the committees there. If I create a committee with a president and a treasurer, that's a permutation. Because if I was president of the world and you were handling my money, that would be a different thing than if you were president of the world and I was handling your money. Okay, so when there's a committee with titles, we have a permutation. But if there's a committee where everybody's equal, we have a combination. Okay, a combination is actually a permutation with the arrangements of order divided out. It's kind of just like dealing with these repeating letters. Okay, we divide out the arrangements that don't do anything. Always deal with restrictions first. Whenever possible, think about the questions in terms of fundamental counting principles. It just usually makes it easier. Often even assign letters, and then you can look at it as a word and try and arrange the letters of the word, even though it's not a word, it's just a string of letters, okay? All right, so it always boils down to kind of three different statements here. When you're reading a question, you want to ask yourself, do I have options? Do I have a lineup? Or do I have a blob? If your answer is I have options, that is usually referring to you're going to solve this by the fundamental counting principle. Okay, if you have a lineup, you need to think about this as a permutation. And then if you have a blob, you need to think about it as a combination. Okay, so let's try a few things here. Number one, the frequency at which a particular remote transmits can be set by selecting a particular pattern on a row of 8 dip switches. Each dip switch can be set to either on or off. A diagram of a bank of 8 dip switches is shown below. Which expression could be used to calculate the number of possible frequencies that can be set for this remote? Now, there are a couple different ways to look at this, but I think the easiest way to look at it is to say, hey, I have options for every switch. So I'm going to go through all my options. Here's my 8 switches. 1, 2, 3, 4, 5, 6, 7, 8. For every switch, I have 2 options. Either I could choose for it to be on, or I could choose for it to be off. Okay, and so that becomes 2 times 2 times 2 times 2 times 2. Okay, and so the answer ends up being 2 times 2, 8 times, which is 2 to the 8. Okay. All right. The number of distinguishable arrangements using all of the letters in the word Alberta. Well, I have 7 letters in Alberta, so that'd be 7 factorial. Right? Just for clarification, why am I doing that? I should just not assume here. 1, 2, 3, 4, 5, 6, 7. Here's my 7-letter word. Okay, I have 7 options for the front guy because I have 7 letters available to me. Then I have 6 options because I've already used a letter. When you get this word arrangement, arrangement implies it's like you're using Scrabble tiles, okay? So once you've used a letter, you can't use it again. So that's why I immediately said 7 factorial, because I know that that's going to be 7 times 6 times 5 times 4 times 3 times 2 times 1, okay? But I also have repeating A's. So I'm going to have to divide out those repeating A's. So that'll actually be 7 factorial divided by 2 factorial. And that's going to give me B, 2,520. Okay, solve for N. Now, before I do this one, what I want you to understand is just with numbers before we deal with the letters. So if I showed you 10 factorial divided by 7 factorial, okay? Now I know you could type that in your calculator, but that's not the purpose right now. What I want you to see is 10 factorial could be written as 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, what's the point? The point is that it's just 7 factorial. So I could say it's 10 times 9 times 8 times 7 factorial. I can stop expanding anytime I want, as long as I put the factorial sign back. Okay, so how would that be helpful in this question? Well, this would end up being 10 times 9 times 8 times 7 factorial over 7 factorial, and my 7 factorials will divide each other out. So then I'm just left with 10 times 9 times 8. 8 times 9 is 72, times 10 is 720. Okay, I could actually do all that in my head without a calculator. So same sort of setup here. So what you want to do is the bigger guy, the larger number, needs to get expanded down until he meets the smaller number. And that's when you put the factorial sign back. Okay, so who's bigger, n minus 2 or n minus 3? Well, if you're unsure of that, stick a number in for n. If n was 10, I'd get 8 and I'd get 7, right? So the top guy there is the bigger number. So I'm going to expand n minus 2. What comes after n minus 2? That'd be n minus 3. So I'll go n minus 2 times n minus 3. Now I want to stop at that n minus 3. That's why I put the factorial sign back. Okay. Now my n minus 3 factorials will divide each other out. Okay. And I'll be left with n minus 2 equals b. Well then, if n minus 2 equals b, I can just add 2 to both sides and say that n will be b plus 2. Okay. All right. Now, a student is classifying the following problems, which may be solved either by using permutations or combinations. For each problem, use a 1 to indicate that it can be solved using permutations, and a 2 to indicate that it can be solved using a combination. So you're going to go through each of these scenarios and say, does changing the order produce a different result? Okay, so determine the number of 3-letter arrangements. As soon as you see the word arrangement, order does matter, so that is a permutation. Okay, determine the number of 4-person committees. The key word here is committee, and there's no titles involved in the committee. That would be a combination. Determine the number of arrangements. Again, see that word arrangement, okay? So putting War and Peace here and A Christmas Carol here is a different arrangement than putting A Christmas Carol here and War and Peace here, okay? And then determine the number of 3-digit security codes that can be formed from the digits 0 through 9. Is a security code 123 different than a security code 321? Yes. Okay. So actually, the only combination in that guy was B. Okay. So I would key this as 1, 2, 1, 1. This is actually a very common type of diploma question for numeric response. Okay. Okay, while determining the solution to a problem, Ruby determined that 43 choose 17 gives the same result as 43 choose x, where x is not 17. The value of x in 43 choose x is what? Now, this is a principle that they're testing. It's just a direct knowledge thing that they're testing. And here's what the principle says. I don't know if you remember it or not. But essentially, I'm just going to pick a smaller number for a sec. If I said 10 choose 2, 10 choose 2 is the same as 10 choose 8. Now, if you don't believe me, go type those things in your calculator and see what happens, and you'll get the exact same number. The reason I know it's the exact same number is because 2 plus 8 equals my n. Okay? So algebraically, we often say n choose k will always equal n choose whatever n minus k is, okay? Now, why? Well, I can put this in perspective for you. It's kind of a morbid example, but it often helps to click. If there was 10 people in a room and I walked in and said, hey, I'm gonna choose 2 of those 10 and I'm gonna kill you. Isn't that the same thing as me walking into a room and saying to the 10 people, I'm going to choose 8 of you and let you live? Okay, it's the same grouping. It's just looking at it from 2 different perspectives. Okay, and that's why they always end up being the same number. Okay, so once we understand that, this question becomes super easy because really all we're trying to do is figure out what 43 minus 17 is. Okay. As long as the two R values add up to the N value, they will always equal each other. So the answer is 26. Okay. All right. When selecting 3 different songs to include in a presentation, Joseph considers a total of 8 songs from his MP3 player. In his list of possible songs, he has 3 rock songs, 3 country songs, and 2 classical songs. He plans to use a classical song to conclude, but he has no restrictions on the first 2 songs. Okay, so draw yourself out. Here's my 3 songs. I have 2 classical songs, so I know that I want to end with a classical song, so I'm going to put a 2 in the back. Because this is a presentation, there's order to the presentation, so whether I choose to start with a rock song and then a classical song, or I choose to start with a classical song and then a rock song, that does change the presentation. Okay, so this is a permutation. I'm approaching this a little bit from a fundamental counting principle as well, because I have options for each of the 3 songs, and I think that's just a better visual. Okay, so at the back, I know I have 2 options. Now, I have no other restrictions, so except that I've used a song. I probably don't want to use that song again, right? So now I have essentially 3 and 3 and 1. So I have 7 songs left to choose from, and I need to pick 2 of them. Okay, so that'd be 7, pick 2. That would take care of these first 2 songs. Okay, because remember, I always have to deal with the restrictions first. That's why I went right to the back. Okay, doesn't matter where the restriction is, you have to deal with it before you deal with all the stuff you don't care about. Okay, and when I say deal with all the stuff you don't care about, just for clarification, I mean deal with all the stuff that there's no restrictions on. Okay. The back of a credit card shows a 3-digit card verification number, also known as, or card verification code, known as CVC. The digits can be any number from 0 through 9, and the digits may be repeated. If the number of digits in the CVC was changed from 3 to 4, which actually they did with American Express. American Express has 4 digits, whereas Visa and MasterCard have 3 digits. Just in case you ever want to know, I'm a wealth of useless information. The number of possible CVCs would increase by. Okay, so I have essentially, here's my 3-digit one. And I'd have 10 options for each of those, right? So that would be 10 times 10 times 10. So that'd be 1,000. That's a really bad 0. But then for the 4 guy, I'd have 1, 2, 3, 4. That'd be 10 times 10 times 10 times 10. That would be 10,000. Now, the question is, how much does it increase by? So I've gone from 1,000 to 10,000. I have increased by 9,000. Okay, so the answer is 9,000. Is that okay? Okay. A magazine publisher is planning a photographic layout to show how 12 different outfits are possible by combining 1 shirt, 1 jacket, and a pair of pants. If 2 different jackets and 2 styles of pants are used for the photographic layout, what's the minimum number of shirts required to show that there are 12 different outfits? Okay, so this is a fundamental counting principle question, but I don't know one of the options. I know the answer. I know something times something times something has to equal 12. Okay, so I need to backtrack and get one of my somethings. So I'm just going to call that something n. So I have 2 jackets and I have 2 pants. Okay, and then I have n for the number of shirts I need. But then I know that those 3 things multiplied together have to equal 12. So 2 times 2 is 4. Divide both sides by 4. N is going to have to be 3. The next sort of series of questions are what we call pathway questions. Pathway questions essentially say how many ways are there to go from point A to point B. Okay, now the rules around a pathway question, you're not allowed to backtrack, so you always have to be heading towards your destination. So if you look at this picture I've given you, you have to always be going up or to the right. You can never go down, and you can never go left. Okay, now, sometimes teachers get extra fun with pathways where they'll give you holes inside the pathway. That's not part of the 30-2 curriculum, so you won't see those types of questions on your diploma. Okay, now, how am I going to handle this guy then? Well, here's what I need you to see. No matter what pathway I choose, well, let me draw a couple first. How about I could go like this? Okay, that's one pathway I could do. Or I could maybe go like this. There's another pathway I could do. Or I could go like that. Okay, there's so many different ways, and your job is to figure out how many different ways. No matter which pathway I just drew there, certain things have to happen. I need to move up 3 times, and I need to move right 3 times. And so what you can do is you can think about this as a string of letters. Up, 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 right, right, right. I have to move up 3 times and right 3 times. Well, just arrange those 6 letters. That's a 6-letter word, so that'd be 6 factorial. But then I have repeating U's and repeating R's. So I'll divide out my repeats. I'll divide by 3 factorial and 3 factorial. Okay? Put that in your calculator and you get 20. Just be careful of your brackets. If you're doing this all in one, if you're a white Casio or an older TI, make sure that bottom is in its own set of brackets. Okay, now that's what I think is the easiest way to handle this. Just in case your teacher never taught you that, I will review, there's a counting way as well. And you say, okay, there's one way to get to that spot, one way to get to that spot, one way to get to that spot. Okay, and there's one way to get to that spot, one way to get to that spot, one way to get to that spot. The only way to do that is to just keep traveling along that line. Now, to get to here, there are actually now 2 different ways to get to here, because I can either come from that pathway or I can come from that pathway. There are 3 different ways to get to here, because either I'm coming from here or from here. There are 4 different ways to get to here, because I'm either coming from the 3 or the 1. Next line up, there'd be 3 different ways to get to here, because I'm coming from either the 2 or the 1, which means there's 6 different ways to get to here, either from this 3 or from this 3, which means there's 10 different ways to get to there. And then the last guy, there'd be 4, there'd be 10, and then that would end with 20 ways to get to B. Okay, so if that's the way your teacher taught you and that's a more comfortable way to do it, then go ahead. This, though, I just think is easier because I don't have to lose myself in the pathway. Okay. All right. Okay, so let's try this one. Now, the difference with this guy is I have to get to these intermediate steps. I have to go from A to here. Okay, I can't just say overall how many ways I'm going right and how many ways I'm going down, because if I did that, I'd actually create this big grid that doesn't actually exist. So instead, it becomes 3 little questions. I have to get from there to there, I have to get from there to there, and then I have to get from there to there. And so I have to do this and this and this. Anytime you find yourself saying and like that, in combinatorics questions and in probability questions, you end up multiplying the separate cases together, okay? So if I looked at the first section, I end up having to go right, right, down, down. Okay, so that would be 4 factorial, 4 moves altogether, divided by 2 factorial, 2 factorial. To get to this guy, I have to go right, right, down, down, down. So that's 5 moves altogether, 5 factorial, divided by my 2 R's that are repeating and my 3 D's that are repeating. And then to go from here to here, I'd have to go 3 moves and divide by my 2 downs. Okay. Type all that in your calculator, and you should get 180 ways. Okay, 180 ways. Okay, and then we could also go 3D. Now, although this looks scary, it's not. We're just adding 1 dimension, so we got to go right, right, down, down, and then back. Okay, so right, right, down, down, back. If I wanted to arrange the letters in that word, I'd go 5 factorial, divided by 2 factorial, 2 factorial. Okay, and that would be 30. Okay, a fruit salad is to contain 1 green fruit, 2 different yellow fruits, and 3 different red fruits. The number of possible fruit salads that can be made from 2 green fruits, 5 yellow fruits, and 9 red fruits. Okay, so the first thing you're asking yourself is this, do I have options? Do I have a lineup, or do I have a blob? Okay, essentially with this guy, you have a blob with options, because you're going to choose from the yellow fruits, and you're going to choose from the green fruits, and you're going to choose from, sorry, I forgot my other color. What was my other color? Red. You're going to choose from the red fruits. Okay, so I have 2 green fruits, and I want 1 of them. So that'll be 2, choose 1. I have 5 yellow fruits, and I want 2 of them. So that'd be 5, choose 2. And then I have 9 red fruits, and I want 3 of them. So that would be 9, choose 3. Okay, I want the green fruits and the yellow fruits and the red fruits. So I multiply those options together. 2, choose 1 times 5, choose 2 times 9, choose 3. And that's going to give me 1680. Okay. Okay. There are 14 students, 8 boys and 6 girls, who belong to a particular school's badminton club. The coach randomly selects 2 boys and 2 girls to practice together. How many different practice teams could be selected? So I need 2 boys. I have 8 of them. I need 2 girls. I have 6 of them. Okay. The order on a team doesn't change anything. Nobody has a title here, right? So whether I get pulled to be put on the team and then you get pulled to be on the team, or you get pulled to be on the team and then I get pulled to be on the team, that's still the same team. Okay, so I'm using combinations. It'd be 8, choose 2, and 6, choose 2, and I'd multiply that together. So that gives me 420. Okay. All right. A high school volleyball coach is selecting members for the volleyball team. There are 7 power players, 6 middle players, 3 right sides, and 4 setters trying out for the team. The coach must select the following players. I need 4 power players, 3 middle players, 2 right sides, and 2 setters. The number of different teams that the coach can select. Well, you don't need to know anything about volleyball to do this question. You just match up. There are 7 power players, and I need 4 of them. So that's 7, choose 4. There are 6 middle players, and I need 3 of them. That's 6, choose 3. And you just keep going down that line, multiplying everything together. Okay, so we end up with 7, choose 4 times 6, choose 3 times 3, choose 2, and then times 4, choose 2. Go ahead and multiply all that together. Make sure you're a good button pusher. You should get 12,600. Okay. Okay, let me get the ink off there. In the Braille system, each Braille consists of a 6-dot position. Dots can be raised to represent letters, digits, symbols, or common letter combinations. The Braille character for the letter V is shown below. Dots that are raised are represented by solid dots. So in this example, I have 6 spaces, and I've raised these 4 dots here. Okay. The number of different Braille characters that have 4 of the 6 dots raised. Okay, well, that means I'm looking at any 6 of them, and I want to choose 4 of them. Okay, so it just ends up being 6, choose 4. Okay, now lots of kids look at this question and they say, hold on though, a different arrangement is going to be a different letter. So why isn't this a permutation? And the reason you have to think that through, I totally agree with you that if this one was shaded, it would be a different letter, but that's the point. If you said 6P4, you're saying, I'm just going to switch to ink here. Give me 1 sec. You're saying that if I raised this one first, and then this one second, and then this one third, and then this one fourth, that's a different letter than if I raised this one first, this one second, this one third, and this one fourth. Do you see what I'm saying? Like, they've all been raised already. The order of how you raise those 4 doesn't change which 4 are raised. So we're looking at which 4 are raised, and that's why it's a combination. I have 6 options, and I'm going to choose 4 of them to be raised. Okay, hopefully that helps a little bit. So 15 altogether, and that was just 6 choose 4. Okay, the following symbols are selected and arranged to create various code words. No symbol can be repeated in a code word. Okay, which of the following calculations could be used to determine the number of possible code words that could be created when at least 8 symbols are selected and arranged? Okay, so I only have 10. So when I say at least 8, that means 8 or more. So I could choose 8, I could choose 9, or I could choose 10. 8 or 9 or 10. Anytime you find yourself saying or, you're going to add those separate cases together. Okay, so if I chose to say this symbol and then this symbol, is that a different code than if I went this symbol and then this symbol? And the answer to that is yes, it is. So this is a permutation, not a combination. Okay, so we can take out all the ones that use C. So that's a kind of a 50-50 card right now. We can take out C and D because those guys are combinations. Okay, then we're looking at, do I add them together or do I multiply them together? And we just said this is an or. I can do 8 or 9 or 10. I'm not doing 8 and 9 and 10. When you say and, that's when you're multiplying them together. When you say or, you're adding them. Okay, so because this is an or situation, I would be adding them and the answer becomes A. Okay. All right, a 5-member committee is to be formed from a selection pool of 9 men and 6 women. How many ways can this be done if the committee must involve at least 1 woman? Okay, there are 2 different ways to look at this, and I'm going to show you both. I could say, okay, I want 1 woman or 2 women or 3 women or 4 women or 5 women. Now, you have to remember that each one of those also has to be a 5-person committee. So if, for instance, you want 3 women actually means I need 3 women and 2 men. That way I get a 5-person committee. Okay, so 1 woman, 2 women, 3 women, 4 women, 5 women. That would be the easier one, which I'll show you in a second, is going to be total minus no women, but I'll deal with that guy in a sec. Here's the first one. Okay, so in this guy, I have 6 women and I want 1, and I have 9 women and I want 4. That gets me my 5-person committee with 1 woman and 4 men. Or, so I'm going to add these guys together, I want 2 women and 3 men. Or I want 3 women and 2 men, or I want 6 women and 1 man, or I want 5 women and no men. Okay, so I'd have to type all of that in. This is a great example, although this is long, this is a great example of and versus or. Okay, so you can see I'm multiplying when I need the and portion. I need 1 woman and 9 men to form that 5-person committee. Okay, or so that's where I add, I need 2 women and 3 men. Okay, and so when I'm anding, I'm multiplying, and when I'm oring, I'm adding. Okay, that should get you a total of 2,877. Then I'm going to show you the easier way. The easier way would be total minus no women. This is a concept called the complement. The complement says this: if it's a really, really long question, sometimes the easier way to do it is to take the total and subtract the thing you don't want. And by subtracting the thing you don't want, what you end up with is what you did want. Okay, and so the only thing in this scenario, if I want at least 1 woman, the only thing I don't want is no women. So I could take the total and subtract no women. Okay, so for the total, I have 15 people altogether, 9 men, 6 women. So I'd have 15, choose 5, that gets me any 5-person committee. And I'm going to subtract the amount of committees that don't involve any women. So that would be 6, choose 0, no women, and 5 men, which is the 9, choose 5. Okay, and then if I type that in my calculator, you will notice you get the exact same answer. Okay, so to me, this one's easier because it's less button pushing. But for you, it's whichever one makes most sense. Okay, whichever one makes most sense to you, whichever is the better visual for you, that's what you want to do. Okay, all right, so this actually concludes combinatorics, counting methods. Hopefully this is feeling good. Hopefully you're can see a little bit more of the visual than when we started this process. So then we'll see each other for the next video. The next video we will deal with is probability. Okay. All right. Take care, guys.